Hello everyone, Mr. Linder here. Let's talk about hemostasis. So hemostasis is the process of fixing a broken blood vessel. If we were to not fix broken blood vessels, we would experience hemorrhaging, which is the loss of blood. So this is an important protective function in the human body to ensure that we don't have rapid amounts or large amounts of blood loss. In order to have hemostasis occur properly, there are three major processes or steps to consider. The first major process is vasoconstriction. And so we'll need to discuss that. The second thing that's going to take place in hemostasis is the platelet plug or platelet aggregation. And the third thing that we want to take a look at is coagulation, or the formation of the actual fibrin clot. So vasoconstriction, platelet plug, and coagulation are the three main events that we want to take a look at to fix a broken blood vessel. Vasoconstriction is going to begin immediately, and that's basically the shrinking or constriction of the blood vessels to prevent the loss of blood. And there are various chemicals that are going to be involved in vasoconstriction. Platelet plug is basically a positive feedback mechanism that's going to allow platelets to stick into the opening of a broken blood vessel. And again, that's going to help us prevent blood loss. And then finally, coagulation is a multi-step process in the formation of what we call fibrin, which fibrin is a protein that's going to interweave within the damaged area and again, help us to prevent blood loss in a more thorough process. So rather than just simply narrowing the vessel or sticking platelets in there, we're going to reinforce that structure with fibrin. And so we need to go through these various processes and look at the various chemicals that are involved. Again, understanding that vasoconstriction and the platelet aggregation really are just temporary hemostasis, whereas the formation of fibrin is going to be a more permanent fixture before we get cellular regeneration and connective tissue development to make sure that we fix that broken blood vessel. So what are some of the things that we need to take a look at when you're thinking about this idea of hemostasis? So when a vessel breaks, the first thing you want to understand is that there's going to be collagen proteins that enter into that damaged area. So if this is the broken area of the endothelium or of the layers of the blood vessel, what you're going to see is you're going to see these collagen proteins that are going to be exposed and extending out into that damaged area. Once you have collagen in that damaged area, you'll begin to see platelets adhering to the collagen. Platelets actually use an integrin protein so that they can adhere to the collagen. And what's going to assist the platelets sticking to the collagen is a factor called the von Willebrand's factor. And von Willebrand's factor is actually produced by these damaged endothelial cells. So we have endothelial cells here, and you can see them all along here. And these are producing this VWF, or von Willebrand's factor, and that's going to assist in the platelets adhering to the collagen. So let's take a further look, and so let's zoom in on this. So on this particular diagram, what you're actually looking at is first a normal or healthy blood vessel. So here you can see the endothelial layer. That would be known as the tunica intima. And then you're going to have a smooth muscle tissue deeper in the wall. So that's going to be your tunica media. And then, of course, you'll have a tunica externa layer. So in this normal vessel, you can see the collagen fibers are not exposed to the plasma. So this would be the plasma location. And so here we have free-floating platelets, and you're going to have other red blood cells and white blood cells flowing through the vessel, and of course everything else that's mixed into the plasma. And so here we have our endothelial layer. So this is the endothelium, and it's intact, not damaged. And so you'll notice in this particular diagram that the platelets aren't sticking to those endothelial cells. And so we want to talk about what's happening there. If we look at the next diagram, you'll notice that this is a damaged vessel. Okay? And so we're going to talk about what are the chemical signals that are being released that's affecting the physiology when there's actually damage to the blood vessel. And then the third picture is actually the formation of fibrin. So this is looking at the idea of coagulation. So let's start with the normal vessel. So why is it that platelets aren't normally sticking to a normal blood vessel wall? Why do platelets not normally stick to the endothelium? Well, endothelial cells are producing chemicals that are actually going to prevent the platelets from sticking to the healthy endothelium. One of the chemicals that is produced is known as prostacyclin. So this PGI2, this is prostacyclin. And prostacyclin is a prostaglandin chemical. It's actually made from phospholipids. And this prostacyclin is preventing platelets from aggregating together. So it's preventing platelets from sticking to each other. Prostacyclin can also act as a vasodilator. And so vasodilation is going to help to keep the vessel open and allow for the plasma and formed elements to flow freely through the vessel. You also have nitric oxide that's being produced by the endothelial cells, and nitric oxide is also a vasodilator. So prostacyclin and nitric oxide are, again, keeping the vessel dilated so that the plasma and the formed elements can flow through freely. Another thing that you see in a normal vessel is you have enzymes that are embedded in the plasma membrane of the endothelial cells. These enzymes are referred to as CD39 enzymes. So this is an enzyme. And the CD39 enzymes are important to break down adenosine diphosphate, so break down ADP into adenosine monophosphate. That's important because ADP is actually a platelet aggregator. Okay. So ADP is one of the chemicals that is going to cause platelets to stick to each other. So we want to make sure that we're breaking down any free-floating adenosine diphosphate into adenosine monophosphate so that platelets aren't signaled to aggregate or stick together. So in a normal vessel, it's the prostacyclin, the nitric oxide, and the CD39 enzymes that are working together to vasodilate the vessel, to prevent platelet aggregation, and to allow the plasma and the formed elements to flow freely through the cardiovascular system. So what happens, though, when you have a damaged vessel? So looking at this damaged vessel, again, one of the first things you want to notice is these collagen proteins are now exposed to the plasma. So we have these collagen proteins, and I can draw a few out like this. We'll extend them out into the damaged area. Those collagen proteins are going to interact with the platelets. So platelets that are in the plasma are going to begin to stick to the collagen. And so what are they adhering to? Well, they're adhering to these proteins that are part of, you can see them in blue, these proteins that are part of the collagen. And these, of course, are the von Willebrand's factors. And so the von Willebrand's factors allow platelets to adhere to the collagen fibers. Once the platelets begin to stick, you're going to see a positive feedback loop. So we're going to see positive feedback. And what that basically means is that as one platelet sticks to the area, so as this platelet begins to stick to the collagen proteins, that's going to attract other platelets. And so we have another platelet sticking to the collagen, and then that's attracting another platelet, and so forth and so forth and so forth. So we've got this positive feedback loop that is taking place. As platelets stick to the collagen, they begin to release chemicals and they attract more and more platelets. So what kind of chemicals are the platelets releasing that is going to help us in this hemostasis process? So the first couple chemicals to take a look at are thromboxane A2. So that would be thromboxane. Thromboxane is another type of prostaglandin. Only in this case, this particular prostaglandin, unlike prostacyclin's a vasodilator and it prevents platelet aggregation. Thromboxane is being used as a vasoconstrictor. So this is where we start to see that first process of hemostasis, the vasoconstriction. And this happens rapidly. This happens immediately upon damage to the blood vessel wall. You start to see the release of thromboxane. You also see 5-HT. 5-HT is serotonin. So serotonin. Serotonin is also a vasoconstrictor. And so with serotonin and thromboxane, you are shrinking the size, right? We're shrinking the diameter of the blood vessel. And so that's going to limit how much blood flows through the vessel and how much fluid loss you're actually going to have. What else is going on though? Well, thromboxane, serotonin, adenosine diphosphate. Okay, so this one right here, adenosine diphosphate. And then this chemical right here, PAF, that's platelet activating factor. All of those chemicals are acting as platelet aggregators. So platelet activating factor, adenosine diphosphate, your 5-HT, your serotonin, and then your thromboxane, so TXA2. All four of these are for aggregation of platelets. Okay? So aggregation of platelets or platelet aggregation. That means the platelets are going to stick to the von Willebrand's factor on the collagen, and we've got this positive feedback loop. And as another platelet sticks, it degranulates, it opens up its vesicles, and it releases more chemicals. So thromboxane and serotonin are your primary vasoconstrictors that you immediately see happening when you damage a blood vessel. And then you use platelet activating factor, adenosine diphosphate, serotonin, and thromboxane to attract more and more platelets to that damaged area so that you can continue with this positive feedback loop and eventually form what we call the platelet plug. So platelets are sticking into this opening and giving us that temporary fix so that we don't lose blood. But somehow we got to reinforce those platelets. And so that's where that coagulation process is going to come into play. Another chemical to make note of is platelet-derived growth factor. And platelet-derived growth factor is also produced by the platelets. And the role of platelet-derived growth factor is to activate fibroblasts. And fibroblasts are the cells that produce collagen, elastic, and reticular fibers that we see in connective tissue. So fibroblastic cells are in essence producing connective tissue that is in essence going to form what we call scar tissue. And so as we are repairing the broken blood vessel, we are essentially also repairing the walls of the blood vessel with connective tissue and thus scar tissue formation. Platelet-derived growth factor also is going to enhance the activity of the smooth muscle cells in the wall of the blood vessel, and that's going to promote healing of that smooth muscle that's been damaged in the blood vessel wall as well. So this particular table that you're taking a look at is really a summary of the chemicals that we were talking about in the vasoconstriction and the platelet plug pathways for hemostasis. So here we can see von Willebrand's factor and its role in hemostasis. Here we have the serotonin chemical. Again, notice that serotonin has two roles, platelet aggregation and vasoconstriction. If you take a look at thromboxane, thromboxane also has those two roles, platelet aggregation and acting as a vasoconstrictor. And then we have our other chemicals, adenosine diphosphate and platelet activating factor, which are involved in platelet aggregation. So all four of them are involved in platelet aggregation, and then serotonin and thromboxane are your vasoconstrictors. So this is a nice summary table for what's taking place in vasoconstriction and the platelet plug. What about coagulation, though? What about the production of fibrin? So this is a bit more complicated because in the coagulation process, where you're actually producing that fibrin protein, you're looking at several different pathways. So the pathways are referred to as the intrinsic pathway and the extrinsic pathway. The intrinsic pathway is using a chemical that is based within the blood plasma. It's one of the clotting factors. This is factor 12, which is known as the Hagman factor. And so the Hagman factor is going to be the precursor for the intrinsic pathway. And if you follow the pathway, so if we go down the line here, if we follow the pathway, eventually you're going to get to the production of fibrin. So intrinsic pathway leads us to the production of fibrin. But the extrinsic pathway also leads us to the production of fibrin. The extrinsic pathway begins with a chemical that starts essentially outside the plasma. And so we call this tissue factor, factor 3. It's also known as tissue thromboplastin. And if you follow this pathway, so if we follow the pathway, okay, eventually you're going to get yourself all the way to fibrin again. So whether you take the intrinsic pathway or the extrinsic pathway in coagulation, both pathways lead you to the production of fibrin. Notice that both pathways, intrinsic or extrinsic, lead you to factor 10. So clotting factor 10, also known as the Stewart-Prower factor, is part of what we call the common pathway. So intrinsic pathway leads us to the common pathway. Extrinsic pathway leads us to the common pathway. So both of these are going to lead to the activation of the Stewart-Prower factor, which is eventually going to give us fibrin. So what I would like to do is show you the different clotting factors, and then we'll come back and we'll go through these two pathways for the production of fibrin. So this particular table lists the clotting factors. Notice that the Roman numerals go up to 13. So this is clotting factor number 13, starting with number 1 all the way to 13. However, there's only 12 factors. And so that might throw you off a little bit, but that's because there's no Roman numeral number 6. Okay? During the discovery of clotting factors were numbered based on their discovery and not their location within the pathway. So the first clotting factor was fibrinogen. Fibrinogen is the protein that is going to become fibrin. So that was the first clotting factor discovered in the process of coagulation. So it was listed as factor number 1. As the discoveries were being made, factor number 6 was discovered. However, it was later determined that it actually wasn't a new clotting factor. In essence, clotting factor number 6 is really just the activated version of proaccelerin. So proaccelerin becomes what we call accelerin. And that's what they were originally referring to as factor 6. But since it's just the activated version of factor 5, it really should have been labeled as factor 5A. So therefore, it's not a new clotting factor. It's just the activated version of a clotting factor that was already labeled. So when you look at the numbers, yes, it goes up to factor 13. However, there's only 12 factors. You'll also notice that most of these chemicals that are referred to as clotting factors really are cofactors, okay, or they are enzymes, okay? So they're working within the pathway in order for us to actually produce the fibrin protein. So really the main two clotting factors are going to be prothrombin and fibrinogen as part of the common pathway. The rest of the factors are cofactors or enzymes. You'll notice even calcium, which is an ion, right? Calcium's an ion, but it's listed as a clotting factor. Okay, so there are a variety of proteins that are used within the coagulation pathway. So let's take a look at the two pathways, the intrinsic and extrinsic pathway, and talk about how we get to the formation of fibrin. So this is just another way to represent the two pathways. This is the extrinsic pathway, so that's going to start with factor 3, which is tissue factor coming from outside the blood plasma. And then this is the intrinsic pathway on this side. So this is starting with factor 12, which is the Hegman factor. And then notice that both pathways lead to the activation of factor 10. So factor 10 is that Stewart-Prower factor, which is the beginning of the common pathway. So extrinsic, intrinsic lead us to common pathway. Common pathway leads us to the production of fibrin. So let's take a look at each pathway. So what's going on in the intrinsic pathway? Well, the first thing that has to happen in the intrinsic pathway is you have to activate factor 12. So what they're showing you in the diagram is that factor 12 becomes activated factor 12. You could have listed it as 12A if you wanted to, activated version of the Hegman factor. So what is actually activating the Hegman factor? Well, typically it's collagen. It's the same concept that you see with the platelet plug. Exposure to collagen, this plasma protein, this enzyme within the blood plasma becomes activated and it starts the coagulation pathway. But notice that coming in contact with glass or other objects is going to start the clotting process. This is why if you take a blood sample, if you take blood and you put it into a glass tube, if you don't have some sort of anticoagulant in that glass tube, the blood's just going to clot in that tube. Same thing if you're trying to run blood through tubing, you're going to have anticoagulants in that tubing, or blood is just going to clot because that Hegman factor is going to become activated and it's going to start the production of fibrin, which is clot formation, what we call coagulation. So once the Hegman factor, though, becomes active, what happens? Well, factor 12 activates factor 11. Okay, so factor 12 activates factor 11. Factor 11, once it's activated, is going to activate factor 9. Factor 9 has another name. It's called the Christmas factor. That's interesting because there's a medical condition known as the Christmas disease. So we'll come back to that. It's a form of hemophilia. So 12 is activating 11. 11 is activating 9. Once you have active factor 9, that's going to activate factor 10. Okay, so in order to get to the common pathway, it's 12, 11, 9, and then it activates factor 10. Once you activate factor 10, the Stewart-Prower factor, then you're going to go on to activate prothrombin. Prothrombin is factor 2. And so factor 2 is going to become active, and we call that thrombin. We can call it 2A. Okay, so prothrombin becomes thrombin. And then once you have active thrombin, Thrombin is going to convert fibrinogen into fibrin. So fibrinogen is factor 1, and so active fibrin, we can call that 1A. So Stewart-Power factor activates prothrombin to thrombin. Thrombin activates fibrinogen into fibrin, and now we have this protein that is going to reinforce the clot, the temporary clot that we had with the platelet plug, and that is going to reinforce it and make sure that we're not losing blood. You'll also notice that there is factor 13. Factor 13 is fibrin stabilizing factor, and fibrin stabilizing factor is going to help to cross-link the fibrin proteins together and just make that fibrin protein much stronger. So for example, if you had fibrin proteins, that fibrin stabilizing factor is going to cross-link those proteins together, and that's going to make this much stronger. Almost think of it like a chain link fence. Okay? So we're going to cross-link those fibrin proteins together, and it's going to make a much stronger fibrin mesh. So that's fibrin stabilizing factor, or factor 13. So that's the intrinsic pathway. 12, 11, 9, factor 10, the Stewart-Power factor, prothrombin to thrombin, fibrinogen to fibrin. The extrinsic pathway is much shorter. Basically, you take tissue factor from outside the plasma. Basically, it's being released by damaged blood vessel tissue. Tissue factor is essentially activating as a cofactor to turn on factor 7. Okay? So factor 3 is a cofactor, and it's going to be turning on factor 7. Factor 7 becomes activated, and once factor 7 is activated, you can activate the Stewart-Power factor, factor 10. Now you're in the common pathway, so everything else is the same. You have factor 10, which turns on prothrombin to thrombin, and then thrombin turns on fibrinogen to fibrin. You have fibrin stabilizing factor, cross-link the fibrin proteins, and you get coagulation to take place. So it's in the extrinsic pathway, it's 3 activating 7, 7 activating 10. Something to make note of, you'll notice that I didn't talk about every clotting factor. That's because, again, a lot of these are enzymes or cofactors, in the process. So for example, factor 5 is involved, factor 4 is involved. Factor 4 is in essence calcium. Okay? So these other clotting factors are assisting in some of the steps in the intrinsic, extrinsic, and common pathways. But these are the major events that are taking place. So you do have other clotting factors that are involved. But if you were just looking at the ones that directly get you to Stewart-Power factor and get you to fibrin, that's where you focus on intrinsic and extrinsic pathway. Once you have coagulation done and you've produced this fibrin mesh, now you have a reinforced structure that's going to prevent blood loss. This is what that would look like. Okay, so this is the reinforced fibrin structure. Okay, so that's the fibrin clot. And notice you can see blood cells stuck in there. There would be platelets in there. You get red blood cells stuck in there. And that's going to be your clot structure while you have connective tissue and muscle development and epithelial tissue development to fix the walls of the blood vessel. You don't want the clot, though, to remain, so we need to have a process called fibrinolysis. And fibrinolysis is where we break down the fibrin once you no longer need that fibrin mesh. So as the damaged vessel wall begins to repair itself, the clot needs to disintegrate, and the way to do that is to produce an enzyme called plasmin. So plasmin is going to be your enzyme that digests fibrin. So how do you activate plasmin? Well, it comes from plasminogen. So plasminogen is a protein that's circulating in your blood plasma that just needs to be activated into plasmin so that that enzyme can go and begin to digest the fibrin polymer, break it into fragments, and get rid of it. So how do you do that? Well, the activation of plasminogen happens in several different pathways. One of the main pathways is this pre-kallikrein pathway to kallikrein. Pre-kallikrein to kallikrein. So you can see that here. Here's the kallikrein molecule. Here's the pre-kallikrein molecule. This is actually a molecule that's activated by the Hagman factor. So here's factor 12. Okay. So as the Hagman factor becomes active Hagman factor, which is going to be involved in the intrinsic pathway. So I'll write that over here, intrinsic. That's that intrinsic blood clotting pathway. The Hagman factor is also activating pre-kallikrein into kallikrein. Once you have active kallikrein, that can be used as an activating mechanism for plasminogen into plasmin. And so that kallikrein molecule is assisting in the fibrinolysis system. So pre-kallikrein to kallikrein being activated by the Hagman factor, which is also working, though, to produce fibrin in the first place. You'll also notice that kallikrein has other mechanisms, and so it's involved in things like the renin-angiotensin system and the complement system for immunity, but for this particular purpose, we're talking about fibrinolysis. Another important pathway is the activation of something called tissue plasminogen activator. So tissue plasminogen activator, or TPA for short, is another molecule that can convert plasminogen into plasmin and then allow that plasmin enzyme to digest fibrin. So activation of kallikrein and activation of tissue plasminogen activator are the two main mechanisms for producing plasmin so that you can break down that fibrin mesh. If you were to stop coagulation, then we would be talking about anticoagulants. So I want to move ahead here and show you some other diagrams. First off, before we get into the anticoagulants, this is just a nice summary diagram for the chemicals that we looked at in the coagulation pathway. So here we have things like prothrombin. Here we have fibrinogen, fibrin stabilizing factor, calcium that's involved in blood clotting. So there's a lot of different things listed. Here's tissue factor listed on here. There's a lot of different chemicals listed as a nice quick summary for what's going on in that coagulation pathway. As far as anticoagulants go, I want to talk about several types of anticoagulants and also look at some of the diseases that would affect blood clotting. The first thing to consider would be anticoagulants that are released from endothelial cells. Endothelial cells can produce an anticoagulant called heparin. We also see it produced by some of our white blood cells. Heparin actually activates a liver protein known as antithrombin. So we actually have a protein called antithrombin. And antithrombin, although it doesn't directly inhibit thrombin, what antithrombin does is it blocks factors 9, 10, 11, and 12, which obviously are intrinsic and common pathway factors. And so that's going to prevent us from activating prothrombin to thrombin. So antithrombin, which is activated by heparin, is eventually going to stop the activity of thrombin, and therefore you are not having coagulation take place. Another endothelial chemical is known as protein C. Protein C has several functions. Protein C can activate tissue plasminogen activator, so it can activate TPA. It also can inhibit clotting factors 5 and 8. And so anytime you're inhibiting some sort of factor within the coagulation pathway, you're going to stop clotting. And then also if you're activating tissue plasminogen activator, you are activating plasminogen into plasmin, and plasmin is digesting fibrin. So you are preventing clotting from taking place. Another way to prevent clotting is through fibrinolytic drugs that are used to prevent clots. A good example of that would be streptokinase. Streptokinase is actually a bacterial enzyme, and this bacterial enzyme is used to activate plasminogen. So streptokinase can activate plasminogen, and we know that plasminogen now becomes plasmin, and plasmin is that digesting enzyme of fibrin. So that's going to act as an anticoagulant. That benefits bacteria when they're trying to get through tissue spaces and clots are forming. They can produce this streptokinase, which is going to basically, again, activate plasminogen to plasmin and act as an anticoagulant. Another way that this might work is through what we call recombinant tissue plasminogen activator. A good example of a recombinant TPA is one called activase. And so activase is man-made, and we introduced that into the system to activate plasminogen, again, into plasmin so that we can digest fibrin. Some other examples are antiplatelet aggregation agents. A good example of that was the prostacyclin that we talked about earlier. Prostacyclin, we know, is a type of prostaglandin. It's actually produced by healthy blood vessels to prevent platelet aggregation. So if you were to introduce a prostacyclin into the cardiovascular system, it would prevent platelets from aggregating and thus would inhibit clotting. Another good antiplatelet chemical is aspirin. So that one's listed on the table here. Aspirin, or acetylsalicylic acid. This actually is a prostaglandin enzyme inhibiting chemical. So it inhibits prostaglandin production by inhibiting certain types of enzymes. Those enzymes that it inhibits are called COX-1 and COX-2 enzymes. That stands for cyclooxygenase enzymes. So aspirin is a cyclooxygenase 1 and cyclooxygenase 2 inhibitor. And so if you inhibit the cyclooxygenase enzymes and you're inhibiting prostaglandin production, you can affect things like thromboxane, which thromboxane is a platelet aggregator and a vasoconstrictor. And by inhibiting those prostaglandins, you are thus inhibiting coagulation from taking place. The downside of aspirin is that it does cause gastric bleeds. It does affect your kidneys and can cause kidney damage. And of course, we're talking about increased clot time with any of these anticoagulants. So those are downsides to taking aspirin. There are some non-steroidal anti-inflammatory drugs, what we call NSAID drugs, that have less side effects than aspirin does because they do not inhibit all of the cyclooxygenase enzymes. Typically, there's specific ones like just cyclooxygenase 2 inhibitors, or they may specifically only block cyclooxygenase 1. So there are other options like ibuprofen as opposed to, say, an aspirin. And then, of course, there's a third category for pain relief, which would be something like Tylenol. Tylenol, which is what we would refer to as acetaminophen, is actually a COX-3 inhibitor, so COX-3. COX-3 enzymes are actually found within the central nervous system, and so we don't see those outside cardiovascular effects. We just see the pain relief effects when we use things like Tylenol. Another example of an anticoagulant would be things like coumarin or warfarin, trade name warfarin. These particular medications inhibit vitamin K activity. Vitamin K is actually a cofactor. It's a cofactor for the synthesis in the liver for a variety of clotting factors. So vitamin K is actually used to assist in the synthesis of factors 2, 7, 9, and 10, which again are all produced in the liver. And so without adequate activation of vitamin K, you're going to affect the clotting factor synthesis and thus prevent coagulation from taking place. So those are good. That's a good anticoagulant chemical as well. Some other examples of anticoagulants would be things like sodium citrate, or just citrate for short. Sodium citrate is what we call a calcium chelator. So it combines with calcium. It is a chelating or chelator agent. By binding up calcium, you're preventing that calcium cofactor from being available in the coagulation pathway, and thus you won't get activation of fibrin. And so again, it acts as an anticoagulant. Another good type of chelator is EDTA. EDTA, that stands for ethylene diamine tetraacetic acid, or EDTA for short. EDTA is also a chelating agent. It doesn't chelate just calcium, so you actually can use EDTA as like a heavy metal toxicity chelator, but it can be used to chelate calcium as well. So it's working the same as citrate. Citrate is actually the first chelating chemical that was used to store blood. So early on, when we were developing the ability to transfuse blood, we needed a way to store blood long term. And so by removing calcium from donated blood, by adding a citrate or an EDTA, you can bind up that calcium, and therefore the blood wouldn't clot in the storage bags. And so that allowed us to store blood long term and to have blood banks and to make blood available in hospitals. The last thing to talk about would actually be things like inherited disorders, so genetic disorders that would lead to anticoagulation issues. So probably the best example would be hemophilias. Hemophilia A is the most common inherited blood disorder. Hemophilia A is about 80% of all the inherited hemophilias. And in this particular hemophilia, you do not produce adequate amounts of factor 8. And so without clotting factor number 8, you're going to have obviously difficulties coagulating your blood. So this is an inherited disorder. Another example of an inherited disorder would be hemophilia B. Hemophilia B is lacking the production or deficient production in factor 9. And as I mentioned earlier, factor 9 is also called the Christmas factor. And so hemophilia B is oftentimes referred to as the Christmas disease. And this is named after the first patient, the case study patient, where they discovered hemophilia B. The last name of the patient was Christmas. And so it's a deficient factor 9. There's also a hemophilia C version, much less common, but there's hemophilia C. Hemophilia C is deficient in clotting factor 11. So X1, that would be 11. So deficiency in factor 11. There's also a von Willebrand's disease. So again, an inherited disorder. And in von Willebrand's disease, obviously you're impairing the ability of platelets to stick to collagen. So these are all various types of examples of anticoagulants or inherited disorders that would affect coagulation. The last couple things I want to show you are just some diagrams, some of the things that I already mentioned. So in this particular diagram, this is showing you how aspirin or other NSAIDs would work, but specifically aspirin. Notice it's a COX-1 and COX-2 inhibitor, and so that's affecting these prostaglandin synthesis pathways, and thus that's going to affect platelet aggregation, which is why it's an anticoagulant. This is another diagram, maybe a little bit easier to see what's going on. Here you have traditional NSAID medications kind of working across the board here for cyclooxygenase 1 and cyclooxygenase 2 type inhibition. Acetaminophen. Notice acetaminophen is mostly this COX-3 inhibitor, which is why you don't get the anticoagulant effects with acetaminophen, but you do get the pain relief with acetaminophen. And then the last diagram I want to show you is just a quick little summary of some of the things that we were talking about as it relates to fibrinolysis and anticoagulants. So we were talking about heparin and how it affects antithrombin 3. We talked about tissue plasminogen activator and its role in fibrinolysis. Also, of course, the activation of plasmin for fibrinolysis. And then here we have prostacyclin, which is a vasodilator, but also is blocking platelet aggregation. And that blocking of platelet aggregation is what can make it an anticoagulant. So I hope that helps with hemostasis, fixing broken blood vessels, and all the various chemicals that are involved, and also the various ways that we can digest fibrin clots, and also how we can have anticoagulants work within the cardiovascular system. I hope that helps. Take care.